Go.
So, as Keisha said, we had some real fireworks on the 4th. And I'm not talking about the terrestrial fireworks, but 500 million miles away, as the Juno probe was approaching Jupiter, it proceeded with some pre-programmed maneuvers to slow down so that it would be captured by Jupiter. Now, around 9:30 p.m. Monday night, 4th, the Juno probe. Now, do we put up the picture of the probe?
Mm-hmm.
Yeah, you have to move the box there.
Oh, okay. 1 second. You ready?
Is it up?
Oh, sorry.
It's up on the screen share here.
Hold on. Let me take just a second here.
Maybe you want to close the blinds over here to the right, bleaching out
So let's warming it up. So Juno was launched in August of 2011. And the name, unlike most NASA probes, missions, it's not an acronym. Juno is the goddess who was married to Jupiter, who was also the sister of Jupiter. So you had some strange family values.
Except now, we have it with the satellite and Jupiter, the Juno probe. So.
Okay, can you see the solar rays?
Perfect.
Yeah. Yes.
Beautiful.
Okay,
Just stay over to your right a little bit.
this
Right.
one.
Yeah, where you are right now is fine.
Yes. Okay.
All right. So this probe was launched on August 5th, 2011. It was launched towards Mars because we do not have a booster that can send a probe to deep space directly. So the first destination of Juno was to go to Mars, get a gravity assist Mars, and it came back to the Earth, and about 2 years later, whipped around the Earth and got a gravity assist of the Earth and headed towards Jupiter. Now, this probe was the fastest man-made object ever. It reached a speed of 132,000 miles an hour. And as it was approaching Jupiter, the navigation team was in the process of preparing it for what they call the Jupiter orbital insertion. Now, the probe had to turn off all the instruments. It had to kind of stow the solar panels and orient itself so that the main rocket motor would be firing to slow it down. Now, if the motor had not fired, it would have flown by Jupiter and you would have a $1 billion flyby with virtually no data of the mission. So at 9:30 on Monday night, the Mission Control Center at the Jet Propulsion Laboratory in California and another Mission Control Center in Denver, where the manufacturer of the probe, Lockheed Martin, at a separate control center, they detected that the rocket motor had fired. Now, since they had shut down all the instruments, they had shut down the main antenna, the high gain antenna. All they were getting from the probe was just a carrier wave, a dial tone. Now, we don't have the globe here, right?
Yes.
Earth.
Hold
It's old. Very old globe.
Well, that's all right.
Hold on.
Just give me a concept.
Joe coming up with it.
get the whole world in your hands here.
No worries.
So we have a series of receivers on the Earth called the Deep Space Network. One is in Australia, you have one in California, Spain, so that no matter what time of day, we can receive signals from deep space. And the way they could tell that the motor had fired is that there was a small shift in the frequency received by the antennas, a small Doppler shift. And for 35 minutes, the rocket motor fired to slow the probe down from 132,000 miles an hour to about 130,000 miles an hour. And the insertion was so precise that the burn for the rocket motor came to within 1 second of what it was projected to burn, and came within 1 centimeter of their target. So the probe entered what's called a elliptical orbit. It skimmed the cloud top of Jupiter, about 3,000 miles from the cloud cover, and is in a very elliptical orbit that will bring it back towards the planet in about 2 months. So it's like a 53-day orbit, really elliptical orbit. Now, this is the second probe to enter Jupiter's orbit. We've sent 7 flybys. The first being the Pioneer 10 in the early 70s, in 1973. And with each flyby, we've gained more and more knowledge of Jupiter. Now, man has observed Jupiter for thousands of years. We know its orbit, we know its the period of its orbit. In 1610, we first looked at Jupiter through a telescope. And this was Galileo, and he observed 4 objects circling Jupiter. And these became known as the Galilean moons. Now, we've used the observation of the moon to determine things like the speed of light. And I can go through that later. But with the first probe that entered Jupiter's orbit was the Galileo probe. And it entered Jupiter's orbit in 1995. It functioned up to 2003, at which point it was directed to plunge into Jupiter's atmosphere. Now, according to some people, since we've already been there and done that, why do we need another probe? We know the diameter of Jupiter, we know the composition of its atmosphere, we have some idea of where the magnetic field comes from. But just to give you an idea of the size of the planet, is Jupiter up there also? Is a probe?
It was.
Okay, yeah, could you put Jupiter?
Stay to your right though, Joe, because you've blocked it before. Stay to your right.
Must have a bigger head than I thought.
1 second.
But just to give you an idea of the size,
Not scale.
now the Earth has a diameter of 8,000 miles. Jupiter's diameter is 10 times that. It's 88,000 miles diameter. So you could fit, volume-wise, you could fit over 1,000 Earths inside of Jupiter. Now, because it's mostly made up of gas, hydrogen and helium, with trace amounts of other elements, the mass of Jupiter is 300 times that of the mass of the Earth. Now,
Chris on the board.
if you take all of the objects in the solar system, besides the sun, because the sun by itself is 99.5% of the mass of the whole solar system. Jupiter itself is 75% of all the mass of the solar system outside the sun. In other words, if you add up all the planets, Earth, Mars, Mercury, Saturn, Neptune, Uranus, even throw in Pluto, Jupiter's mass is 75% of all of the solar system, like I said, besides the sun. Now, the magnetic field strength of Jupiter is something like 20,000 times that of the Earth's magnetic field. So Jupiter is called the king of the planets for a very good reason. Now, what Galileo, the probe, told us is that there's a very strong radiation belt surrounding Jupiter. And the four main moons, Io is the most volcanic object in the solar system, much more volcanic than Venus or Earth. And what Io does is it spews out all of these elements which are ionized by the magnetic field, so you have a very strong radiation belt around the orbit of Jupiter.
Is that on its ecliptic, or is it all over as a sphere around it? Or
Oh, it's kind of like a donut around the middle,
around its ecliptic?
around the equator. Now, the other thing about the Juno probe, it will be the polar orbit, so it will be able to observe the North Pole, South Pole as the planet spins. Now, the spin of Jupiter, it rotates every 10 hours, extremely fast. So while the Earth rotates every 24 hours, Jupiter, which is 10 times the size of the Earth, diameter-wise, rotates every 10 hours. So you have extremely strong winds. And I don't know if you can see it up there. You see the red dot?
We turned it off.
Oh, you turned it off?
Yeah, because you were just gonna block it, Joe.
Oh, is it up there?
You gotta get putting it up there. You gotta get the box out of the way.
Yeah, but we can wait for
To your right, Joe,
Just stay to the right of the globe, right of the globe on the table.
or the right of the table.
Come on over. You just
Yeah,
kind of
and-
stand right there.
There, now we can see it.
Don't move back and forth.
There you go.
Okay. Stay.
So if you see
Yeah, we see the red dot.
you could fit 3 Earths in that. That's thought to be a hurricane. Now, the Juno probe has 9 instruments which will help define the magnetic field, the gravitational field. There's an experiment to detect the auroras. What is the source of the auroras? There's also an infrared detector. Now, the Juno probe will come within 3,000 miles of the cloud top of the planet. Because the probe will be in the most intense radiation field in the solar system, all of the instruments are housed in a 1 meter cube box, about the size of this desk, of titanium, about a half an inch of titanium, where it will be shielded from the high radiation. Now, even with the shield, the electronics is expected to be fried in about 2 years. So it will only have 30 or 32 revolutions before it's sent plunging into the atmosphere. Now, 2 of the instruments are designed and manufactured by a Texas outfit called the Southwest Research Institute. And one is called the Jovian Auroral distribution experiment, or the Jade experiment. And it will determine the origins and the distribution of the auroras, or the interaction of the charged particles with the upper atmosphere of Jupiter. The other experiment will determine the ultraviolet interaction between ultraviolet light coming from the sun and the particles in the Jovian atmosphere.
Bring down the picture.
Yeah. Now, what will these experiments tell us? Well, what we're looking for is to measure how much water is in the atmosphere of Jupiter. We also are trying to determine whether Jupiter has a solid core, or is the core, some people hypothesize that the core is made of solid hydrogen, which has been so squeezed by the gravity of Jupiter that the hydrogen becomes a metal. It's thought that the spinning of this core and the helium around the core produces the great magnetic field. Now, as the Juno probe comes in closer to the planet with each orbit, using the radio signals that it sends back to Earth, they will be able to measure the gravitational field, and from that determine whether the core is solid, whether it's made of hydrogen, what the composition is. Now, the determination of how much water is in the atmosphere will tell us whether Jupiter was formed in the outer solar system and moved in, or whether the water was distributed by comets and asteroid impacts into the planet. Now, the auroras will tell us the behavior of the magnetic field. So, as one of the key experimenters from the Southwest Research Institute, Dr. Valek, said, is that we don't know exactly what we're going to find, but this is part of the discovery, that the instruments that we have on board will tell us the origin of the planet, whether it was constructed first in the outer solar system, and it will give us some idea of how solar systems are put together. Now, this Juno probe was designed about 10 years ago. And at that time, there was a shortage of a very important isotope of plutonium, because most of the deep space probes that we've sent out to Saturn, the Voyagers, the Pioneer, have been powered by what's called a radioisotope thermoelectric generator. This gives us the advantage of being able to power probes far beyond the reach of the solar power. Now, Juno is however, powered by 60 square meters of solar panels. Now, if you see the picture of the probe, can you put the probe back up? The probe itself is about a little heavier than a typical car, about 3,300 pounds. Most of its size comes from the solar panels. Can you see the panels?
Three of them, I think.
Yeah.
Yeah, the 3 solar panels.
How long are they?
There are a total of 60 square meters.
Oh.
So I think it's like 30 feet
Oh.
for each
Yeah.
of the big ones.
Uh-huh.
Now, guess how much power that produces?
Guess how much what?
500 watt bulb.
He's been listening to the NASA station.
I have been.
He's been cheating.
No, I don't like that.
But if you think about it, you have 60 square meters of solar receptors, and all you're getting is 500 watts.
Wow.
Now, the reason being is that the amount of sunlight reaching Jupiter is 4% of the sunlight that reaches the Earth, because it's 500 million miles away to the orbit. Now, because it's 500 million miles away, radio signals take about 48 minutes to reach Earth one way. So when the probe was being inserted into orbit, we could not change its trajectory or do anything because it takes 48 minutes to send the signal, 48 minutes to come back. Now, the probe itself, with the instruments, will be able to tell us, like I said, the origin of the planet, what the composition is of the atmosphere. Now, a lot of this we can tell from using the Hubble and looking at the spectrograph of the composition of the atmosphere. But because of the intense radiation belts circling Jupiter, we could not determine with great accuracy what the percentage of the elements are. So
Don't walk back around the other direction to the
You're
other.
coming around the front of the table.
Yes.
Oh.
Okay, he got it.
all right.
No, come on over here. Keep going. Keep going. Turn.
But don't block the screen.
All right, there you go.
Yeah,
That's the edge, so don't walk on that side.
all right. Yeah, I gotta get the, there's a navigation team for the Juno probe. By the way, the navigation team, I heard an interview on the NASA TV, and to get out there, because we don't have much satellite infrastructure around Jupiter, they were still using the stars to steer the probe to make sure it got into the right spot. But so you have this new probe, which involved the collaboration of not just the Southwest Research Institute, but two of the instruments are from Italy. So you have the Italian Space Agency collaborating. The rocket that launched the probe, the Atlas V, still uses Russian RD-180 motors. So you have the collaboration of the Russians in the launch. Now, if you watch the insertion into orbit on Monday night, you see the team in Pasadena and the team in Denver collaborating. Now, I might have missed it, but did you catch President Obama congratulating the Propulsion Laboratory?
Not.
Did he mention anything about this probe when he was in Warsaw?
I'm sorry, I didn't.
You mean on July 4th or when?
Or any time this
Anytime,
week?
I don't
anytime.
think the probe is helping us go to war with Russia, so he didn't mention it.
Yeah.
Well, I think the problem is that it was not covered by ESPN.
What did you say?
It wasn't
Sports network.
Because the only station that Obama watches is the sports station. So he couldn't comment on the NASA's maneuver. Now, the whole course of this probe, from launch through its 2-year stay in Jupiter's orbit, be around $1.1 billion, which is about what we spent in Afghanistan every week for the last 15 years.
Every
That's
week.
right there.
Every week, we spent about $1 billion in Afghanistan. Now, this probe will not be looking at the moons of Jupiter in particular, but from the Galileo probe, we were able to see that both Europa and Ganymede and Callisto, the main moons of Jupiter, have what's called the deep oceans. That they have Europa itself, which is an icy moon, inside has a liquid ocean that is estimated to be 60 miles. So the amount of water estimated in the ocean of Europa is estimated to be twice as much as the water in all of Earth's oceans. And it's thought that if there is a heat source inside Europa, that you might have the potential with water and the amino acid, you might have the potential to have life in Europa's oceans.
How big is Europa compared to Earth?
It's about the size of Earth's moon, about 2,000 miles. The other large moons, Ganymede is larger than Mercury, which is about 3,000 miles in diameter. Now, there is projected in the 1920s for a European space mission to go to Europa and dig through the surface and actually send a submarine into the oceans to attempt to see if there's.
You mean for 2020?
But yeah, 2022 is the estimate I say.
You said 1920.
Oh, okay, yeah.
Did you say 60 or 6 miles?
660.
Wow.
660
How do you
miles.
put a submarine down there? That's amazing.
Now, because they have plans to go to Europa eventually in the next 10, 15 years, they don't want to take the risk of having something on the Juno probe contaminate one of the moons. So once the Juno mission is complete, they intend on steering it into the planet itself, at which point you will take readings all the way down until it's crushed by the tremendous pressure. The same thing will happen to the probe that's still circling Saturn, the Cassini probe. Its mission will be complete in about 2 years, and they'll plunge it into the planet Saturn because they also have detected oceans on the moon, one of the moons of Saturn, Titan. But they're not oceans of water, they're oceans of methane. And they want to eventually send probes into the Titan moon to see more up close what's going on in Titan. Now, also, the probe that just flew past Pluto determined that there are oceans inside, there's a huge ocean inside of Pluto itself. And this was totally unexpected, that you have Pluto, which is so far out in the solar system that they thought it would be a dead, icy, miniature planet. Actually is much more active than we suspected. So every time we send something out into space to make discoveries, we come up with some new discoveries that were totally unexpected, which is what we will most likely get once the Juno probe starts activating its instruments in about 2 months. It'll come back closer to the planet, turn on its instruments, and we'll be able to get more detailed readings.
Is
So-
Juno not going to try to take any pictures of Ganymede or Europa at all?
They will, but most of the instruments on the Juno probe are not optical. You have a microwave instrument to detect water. You have other instruments which will detect infrared, ultraviolet. So this probe is not centered on the moons per se, but more on the planet itself. But this shows that there's so much to investigate on Jupiter as well as some of the other planets that missions for these investigations are projected out into the 2020s. And a lot of these missions have been cut back to the bone. So that if we had a revived NASA program, we would not only be funding a renewed set of missions to go out to Mars, Jupiter, and Saturn. But we would be collaborating with nations like China, Russia, the European Space Agency in building and operating these systems. And if you look at what happened over the last week with all of the violence and killing in the US and the threat of war with Russia, if we were to revive the space program and collaborate with nations instead of threatening them, that this is the best of mankind. That if you listen to some of the scientists who are working on these programs, they've dedicated their lives, some 10, 15 years of their lives on one particular mission. And if you look at the group of people that are combined into these missions, if you look at the companies that are involved, like Lockheed Martin, we could transfer a lot of these defense contractors from defense contracts to space contracts. And I'm sure that the scientists and engineers in these programs would much more happily work on space programs than on another defense program.
Sure.
So I think that about covers what I want to cover, and I'll open it up for
Okay,
any
I have a
questions.
question. Oh, is he choosing you? Okay. When you say water, do you mean water like we mean it?
H2O.
Okay,
Yes.
all right.
Now,
Water is water, huh?
yes. Now, the other thing about water is that I saw a paper about 2 months ago where it was estimated that the water on Earth was either deposited by comets or asteroids. And by determining the composition of the water, the isotopic composition, you have heavy water and light water. The ratio of heavy water to light water tells you whether the water came from asteroids or comets. And recently they determined that the water on Earth matches what's carried by asteroids.
What is light versus heavy water?
Well, water, you have an isotope of hydrogen, which is H, with 1 proton. Heavy water has, instead of H, it has deuterium, which is a heavy form of hydrogen, which has 1 proton and 1 neutron in its nucleus.
What about the water that comes from underneath the surface of the Earth?
Well, they still estimate that it was deposited by the heavy bombardment about 3 billion years ago, 3.5 billion years ago, from asteroids. You talking about the groundwater?
No, I'm talking about water that comes up from the mantle.
Okay, yeah.
Emitted by
And
volcanoes.
they found what looks like an underground ocean, like around or just below the Earth's mantle. They say like 3 or 4 times the amount of water there is in all the Earth's oceans.
Yeah, there are all sorts of estimates. But I think the composition is still the same ratio of heavy to light water.
Hi, Joe, you said that the Jade instrument is going to measure the auroras on Jupiter. So,
Right.
and looking at the magnetic field, what's the comparison in terms of the level, the magnetic field here on Earth, and then that on Jupiter, and then how much more visible the auroras may be than maybe comparison to here on Earth, or as that determined?
Well, what they're attempting to determine is whether the auroras are created by the interaction on Earth of the solar wind, which are particles, ionized hydrogen and electrons coming from the sun, interacting with the atmosphere. And you can observe them especially at the poles, because
Earth's poles.
at the Earth's poles.
Right, yeah.
Now, in Jupiter, it's a little different because it's thought that the radiation fields around Jupiter are so powerful that most of the interaction that causes the auroras on Jupiter are coming from the particles in its radiation belts. That's what is hypothesized. So this instrument, the auroral distribution experiment, will determine whether the particles are from the radiation belt or from cosmic rays or from the solar wind, and it will estimate what the distribution of those various particles are.
So they think that the aurora from Jupiter doesn't happen because of magnetic reconnection?
No, it's the interaction of the magnetic field with these charged particles. It's similar to what happens on Earth, but see, the magnetic field on Jupiter is thousands of times stronger than the Earth's magnetic field.
Okay, yeah, that was my question. Okay. So how much stronger?
Joel, is there any, not with this probe, of course, but is there any consideration of how, like, a future probe could, for its energy source, somehow capture some of Jupiter's own radiation, right, as a mechanism to power, instrumentation?
Well, I was just going to mention that I've seen a proposal that we could use the magnetic field, Jupiter's magnetic field, as a particle accelerator. That if we were to build these miniaturized probes and steer them towards Jupiter's magnetic field and have them circle the planet, gaining energy with each orbit,
Right.
and then shoot them out to beyond the solar system, you could accelerate the probe to close to the speed of light. Now, obviously, these would be robotic probes with no men inside. But I've seen a proposal to use Jupiter as a slingshot to the deeper parts of the galaxy.
Oh,
Now,
yeah.
does Europa, is it comparable to moons, Earth's moon, where we know the same side is always facing planet Earth all the time, right? And it would seem that if you had some future vision of habitation on Europa, you want to be on the side that faces away from Jupiter, I guess. It would be just blasted with all this radiation all the time.
Here's the thing that is interesting, I think Keisha said about this movie, that there's an interesting correlation of the Galilean moons, that they have a certain ratio and they interact. So that, Callisto orbits, say, 4 orbits, Ganymede has 3 orbits, so there's a 4-3-2 ratio. Now, what that does is it keeps the moons from being locked to Jupiter's, so they're not like the moon, that they're not tidally locked. Now, the tides on, say, Io are about 100 meters.
Wow.
Io has a solid crust. So just like the tides here are a result of interaction with our moon, you see the tide gauges go up and down a few feet. On Io, the crust moves 100 meters.
The crust.
And that's why it's so volcanically active. And the interaction between the gravity of Jupiter and the gravity of these other moons causes these moons to have a non-circular orbit, so that it's not locked, but the interaction causes the moons to squeeze and expand. And that's what's generating the heat for the volcanoes. Now, Europa has a solid ice crust. And the way they determined there was an ocean there is there are cracks in the crust where water geysers are being shot out, especially through the South Pole.
Geysers, that's exciting.
And it has certain stripes on the surface. So if you were to live on Europa, you wouldn't live on the surface, you'd live in the ocean.
Europa has a similar warping of its crust.
Right, and that's why it has a liquid ocean, because it doesn't receive enough energy from the sun to melt the ice, but it's this squeezing and expanding of its core by the gravitation causes the heat that turns the ice inside into a liquid.
So basically, Io and Europa are the same in that sense, in that they both have massive compression going on, which causes effectively eruption. Just one is hot and the other is cold, is what you're saying?
Right. The only difference is that Io is mostly other elements besides water, where Europa is mostly water.
Other elements like heavy metals, or
Yes, sulfur, there's carbon, oxygen. And this is another reason for the Juno probe, is that it will be able to determine the exact composition of Jupiter's atmosphere. And that will give us a clue of what the other bodies are made of.
do you have any idea why these moons are so like elementally distinguished from each other? Why would one moon just be full of metals and the other moon be full of basically water? And I don't know what the other two are full of. Are they distinct as well?
Well, that's a mystery. Callisto is the darkest object in the solar system as far as an albedo, reflection from its surface. So it's totally different than the other moons. And by the way, there are 67 moons orbiting Jupiter.
Oh,
Right.
what?
Some of them,
Whoa, that's way more than I was told.
right. Well,
Somebody
some of them
lied.
are smaller, like 10 kilometers.
67.
Like
So
an
far.
asteroid, basically.
So forward your bid.
None of them are like asteroids, like Earth has asteroids going around it.
Well, Jupiter has what's called Trojan asteroids that follow in its orbit. And you notice that all the moons have a Greek or Roman
Okay.
names.
Did Jupiter have that many girlfriends?
Well, here's the thing, all of the Galilean,
girlfriend.
well, he did. The Galilean moons, Io and Ganymede and Callisto and Europa, were all lovers of Jupiter.
Right.
And I heard one of the scientists say that the other reason why they named the probe Juno is Juno was the wife of Jupiter, and she had the power to see through clouds to keep an eye on what her husband was doing. And so Io was turned by Juno or Hera into a heifer, and then the heifer was put in the sky. So you have this Greek and Roman mythology all throughout the Jovian system. But see, this is what we still need to determine, whether if Jupiter was formed in the outer solar system, then a lot of the objects in the outer solar system would have been captured by Jupiter as it came in.
Right.
If it was formed closer to like the asteroid belt, then it would have a different composition of its moon. So a lot of this we're still hypothesizing. We don't know.
So the normal thing in our galaxy is to have gas giant planets or dwarf stars like Jupiter much closer to the main sequence stars that they orbit than Jupiter and Saturn are now. So that if you look at the axis tilts of the bodies in our system, right? I mean, if you were to assume any normal kind of a beginning for a solar system, you would expect these, the axes of the bodies to be roughly perpendicular to the plane of that system. The Sun and Mercury and Jupiter are all like that, right? All those three bodies have axis tilts less than 10 degrees, right? You've got Venus, which is apparently a new planet. You've got Uranus, which is some other kind of a special story. But then you've got these other four bodies, which are like Saturn, Uranus, and Mars, and the Earth, which all have this rough 26-degree axis tilt, which means logically that they were captured as a group, right? I mean, so that says that at some point in the past, you've got just the Sun and Jupiter and Mercury sitting there without these other bodies. You figure under those circumstances, Jupiter would be closer into the Sun, not further away, right? So I mean, that's the basic, beginning of the system, right? It's like.
Yeah, but you see, his problem is that if Jupiter was formed close to the Sun,
that is the normal thing in the galaxy.
But that's what it appears now. But just think about it: 89% of the Jupiter's atmosphere is hydrogen, and about 10% is helium. So if it was formed close to the Sun, then the solar wind and heat from the Sun would have blown away the atmosphere. So this is the hypothesis, is that some of these giant planets around other stars were formed outside the snow belt, the snow lines, and came in close to their star. Because in order to have a gaseous giant, you have to have cold.
You got these hot Jupiters that the Kepler mission's looking at. Looking at Jupiters that are closer to their sun than Mercury is, and they're orbiting at amazing speeds.
Like 3 days.
Yeah, just incredibly fast speeds. Almost. Are we seeing that happen where it's blowing away their atmospheres? Or is that even, we don't have advanced enough spectroscopy to see that? Or?
I think it's still open to whether they're going to be absorbed by their main star, because it's not likely that they will last very long that close into the star. But this is another reason why we're looking at Jupiter, because it will give us a clue as to whether it was formed in our solar system or closer in. That will give us some idea of what's going on with these other solar systems.
So you've talked a little bit about the instrumentation, and so the purpose of Juno is to find out exactly how it formed and when, or
right. Well, the other thing is that whether it has a solid core. Because one idea is that you had Jupiter formed from asteroid accretion, and then because it was maybe 10 times this mass of the Earth, it attracted this gas, the other hydrogen, helium around it. Now, Juno will be able to detect changes in the gravity inside the planet, because as it comes in close to its perihelion, it will be able to detect shifts in the gravity, and they do that by detecting the change in the radio signals from Juno to Earth to know the shift in the gravity. Because we had one probe around the Earth which was able to have a certain orbit around the Earth, and every time it came over Antarctica, it would have a shift in its altitude, and they would be able to tell whether it was traveling over ice or over continent over water. So that one of the main experiments for Juno is to determine whether it's a rocky core or is it just hydrogen that's been turned into a metal. So they'll be able to determine whether it's a rocky core. The other thing is it'll be able to determine how much water in the form of gas is in the atmosphere. And that'll tell them whether it formed in the Kuiper belt or whether it formed further out in the solar system, or if there's less water than they anticipated, then it'll tell them that it formed closer into the sun. And then you have the aurora experiment, and you have a couple more experiments, infrared experiment.
So let me ask another question, Joel. It's like in the past, like when we've sent probes to Mars or Jupiter, it's like, we've got like a 50-year span of progress in the way of compute power density, right? I mean, starting off with, those Apollo missions where the best you would have had on board the mission would have been like analog devices and/or things which are basically mini computers, not microcomputers. And, there would be a huge difference between, compute power density available to us now versus even 20 years ago, right? I mean, just you could go out and spend $400 intelligently now and come home with more compute power than anybody could have bought 20 years ago, regardless of money. How much of a difference does that make for something like this Juno probe? Is that something that we could or couldn't have done 15 years ago, say? Or?
Well, before Galileo got out there, this is now 20 years ago, we did have an estimate of how strong the radiation belts were. And the problem with the radiation belts is that they interact with the atmosphere so that even with a space telescope like Hubble, we can have Hubble focus on Jupiter, and using the spectroscopy, we can tell what elements are in the atmosphere. But because of the strength of the radiation belts, it was like a curtain that shielded the planet from these fine measurements. So that it's not so much the computer power, it's the closeness to the planet that gives us more accurate measurements of the atmosphere and the magnetic field. I
mean, just like the math to insert this thing as precisely as they did, is that something we could have done 20 or 15 years ago, or is that something that's just new?
What was
the math?
I said just the compute power to deal with the math involved in inserting this thing as precisely as they did.
No, I think if you look at the Voyager and you look at some of the previous probes, I mean, it's amazing how much we did with so little computer power.
And that's the impression I have. Like the Apollo projects, I mean, there always had to be just human skills, right? I mean,
well, there was an interview last week with a 78-year-old woman who was one of the first employees at the Jet Propulsion Laboratory. And her first job was classified as computer. Because before the explosion of computer power, you would use women as calculators.
Right.
They would do the calculations.
But two whole generations of Asian women sat over their living just sewing ferrite cores together, right? I mean.
Well, yeah, that's different.
Yeah, I'm talking about the actual calculations.
Yeah, they call them calculators, right? I mean, this is in World War II and past World War II.
Yeah.
Right, but there's a new book I haven't gotten a hold of yet called The Rocket Girls. And it supposedly a large number of the eventual engineers at the Jet Propulsion Laboratory were first brought in as computer calculators. And they were able to, in the 60s, to figure out that by the late 70s, the planets would be aligned so that if you were to send a probe to Jupiter and get a boost, a gravitational boost from Jupiter, you could visit all the other planets, Uranus, Neptune, in one shot. So that was the key to the Voyager missions.
Right.
Mm-hmm. What?
But if you look, it's not just computer power, because when I've seen the comparison that your iPhone is 1,000,000 times more powerful than the computer on the Apollo spacecraft.
Right.
But we couldn't get to the moon today.
With our iPhones.
No matter how many iPhones you stack, if you don't have the physical power of a Saturn V to lift the large payload from Earth's gravitational well, it doesn't matter how much computer power.
So we just don't have that anymore?
We don't have to. NASA is now designing what's called the Space Launch System.
Space what?
Launch System, SLS,
Yeah.
which will have about 3/4 of the lift of a Saturn V. And one of the reasons why Juno could not go directly to Jupiter, it had to get the gravity assist, was the Atlas V that launched it simply did not have the lift to put it into orbit around the Earth and then eventually leave the Earth's orbit with enough fuel to get there directly. So we have gone backwards. If you look at the Saturn V at the Space Center, that could lift 100 tons into orbit. The space shuttle could lift 25 tons of payload into Earth orbit.
What about this thing with the airplane with the 400-foot wingspan? What's going to be the launch capability of that?
That's for small satellites. It's what that plane does is it goes up to 40,000 feet and then drops the rocket like a Pegasus.
Right.
And then the plane has a rocket that shoots up to orbit. So you're looking at 1,000, maybe 1 ton payloads, very small payloads.
Hmm.
So it's good to have the computer power, but you have to have the physical lift capability.
Yeah.
And it's just like the power. Galileo probe 20 years ago had a nuclear power plant. So it had a plutonium core, which was a isotope 238, which decays. And as it decays, it produces heat, which using different metals, because of the heat, it induces a current inside the different metals, so you can produce electricity directly from the heat without going through turbines and steam and things like that. The only disadvantage is if you have 1,000 watts of heat generation, you can maybe get 10% of that as electricity. Now that was fine for the Galileo probe. When Juno was designed, there was a shortage of that isotope, so they went with solar. Now the disadvantage obviously is that being this far out, 500 million miles from the sun, like I said, the amount of sunlight hitting the panels is 4% of what hits the Earth.
Portion of angular spread. Right?
And while it was being inserted into orbit, the panels had to be powered down. So it was operating on battery. So that not only was the insertion difficult, but that if you had inserted Juno into orbit and the solar panels were not able to reacquire the sun, you would have a dead satellite. So all these other probes, Cassini, Voyager, I think it's Voyager 1, is now exiting the solar system. And it's still being powered by that of about 10 pounds of plutonium. and it was launched in 1977. So almost 40 years later, it still has power. You can't get that from solar power. And the radio is still able to transmit. We're able to detect its signal, even though it's 17 billion miles away from Earth by now.
Right. When you talk about liquid water on Pluto, has that actually been observed, or is that basically just a logical conclusion of things which they have observed?
Well, this comes from the New Horizon just flew by last year.
Right.
Matter of fact, it was last July. And they expected to see a frozen.
It's frozen solid, right? Which is pretty near absolute zero.
Close. But what they saw is they had surfaces that appeared to be within 100 million years old. So they figured there had to be some kind of resurfacing of the planet. And that had to come from some heat inside the planet. It's thought that that heat is also radioactive elements like uranium, plutonium,
Right.
or decay, even though you have a potassium, which everybody has a little bit of potassium, and potassium 40 is radioactive. So the decay of these radioactive elements
Maybe
produces
after
the heat.
4 billion years, supposedly.
Well, that's the only way they can explain the pictures from
Now, you know the story about Robert Bass and Lord Kepler's heat equations for the Earth?
Let me do this. We can continue the discussion, but let's end the public
Okay.
broadcast here, and then you can continue. So, Joe, if you want to make any closing remarks, we'll have some discussion afterwards.
Oh, all right.
Do you have anything else you want to say?
Well, last Monday night I was tuned into the NASA TV station, and just the excitement from some of the scientists and engineers who were interviewed while they were waiting for the signal gives you a sense of what the best of the United States is. That if you remember what happened when Curiosity landed on Mars, you had groups of youth around Times Square chanting USA, USA, because we had succeeded in a great mission. And if you compare that to what went on in the streets of Dallas last week, those are our options. Either we have man looking to the stars and looking for new discoveries, or we're going to be killing each other, fighting over scraps of dirt on Earth. So that's the importance of the space missions.
Right.